Exactly. Okay, let's start.
Sir, I have two questions on week 3. Can you go to week 3?
Week 3, is it?
Yeah.
Or,
There are few mistakes in the answers also, I think so.
screen visible, right?
Screen is
Okay.
first this question. Okay. This is let the document T equal to this and K equal to this, the possible K singles. Okay, with K equal to 4. 4 ki length kya singles चाहिए. Okay.
Can you repeat yourself? There was a slight interruption. Sorry.
Okay. K equal to 4 is set. It's the size of the word is 4. Okay.
Right.
So suppose I am taking A, D, B, D for 4 letter. Okay. Then I am going to take D, B, A, B. Can you take like that?
A D B D and then D B D A, right?
The A D B D. Why D B D? Why I am going backward? Okay. I shouldn't go backward. No, we go forward.
What do you mean? Okay, no. So tell me what your solution is. Like,
my solution is mistaken.
Okay, so like tell me your what approach you did, and then I'll try to say.
My approach is ADBD, fine.
ADBD, and then
we will go DAB. DAB is also there. DAB. It's in the answer. B is the answer. DAB is there. Okay, fine. Then ADBC. 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 ADBC is also there.
No, wait. So you went from ADBD and then you started at D and did DAB.
DAB.
And then you started at A and then you said ADBC.
Yeah.
No, but why are you starting at only the last position? Like if the, okay, so K equals to 4. So you first took the first 4 positions and then you are starting from the 4th position. Why?
Yeah, like.
But why would you start at the 4th position?
Because sir, in the lecture, I understood like that only, that we are going to start from the 4th position. Or are you using permutation combination over here? That means suppose how many words are there? Now, how many letters are there? 1, 2, 3, 4, if I count it. And for P, that's what? P4. Can you write like that?
No. So this question is very simple. What you have to do is you take the first 4 positions, which you did correctly. So basically what you're doing, you're starting at the first position and taking the next 4. And then you start at the second position and take the next 4. Then you start at the third position and take the next 4. That's it. So what that gives us ADBD. And then you start at D and take 4 positions, which is DBDA. DBDA, right? Which is, it's given in order, the solution. And then you do BDAB, which is this thing. And then you do DABA, which is this thing. And you can see the last is BCDA, which is this thing.
Okay. And in between, sir?
Sorry?
In between, there are so many, no? BADB. From where they got BADB?
BADB. So BADB comes from here, this one.
But I say counting is simple counting.
Yeah, so basically one thing you can check is how many characters are there, how many positions are there in the string? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? But the last one will start at 9. So 9, 10, 11, 12 will be the last 4, what do you call, snippet? I mean, shingle.
Sir, can you zoom in? Then I'm going to tell.
Okay. Better?
Okay, fine.
Okay. So what I am saying is you can start at the first position. You can start at second. Similarly, third, fourth, fifth, sixth, seventh, eighth, ninth. After ninth, you can't go because you need 4, right? So you should have 9 items here. Now 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 position, 9 4 sets. 4.
Okay, 9 points.
Yeah, because you see, you can start at any position and then you have to create the K shingle from that position. So 1, 2,
Okay.
3, 4, 2, 3, 4, 5, 3, 4, 5, 6, and so on.
Okay. Okay. Fine. Fine.
Okay.
The next question. Is Jacob distance. There is error in this question. A intersection we have to find out that I got it. Okay, sir. That is 10.
Sorry. So you're saying there is an error. So let me read it. Given two sets A and B such that A has 20 elements as B has 30 and A union B has 40, then Jaccard is what? Okay. So A union B, we know. What is A intersection B then?
A will be equal to A plus B plus A intersection B.
Right.
Minus A intersection. Then I'm going to get A intersection B. That I got 10.
Okay.
Right, sir?
Mhm.
Then Jaccard distance is A intersection B upon A union B. The value. Determinant of A intersection B upon A union B.
Right.
So 10 will 40. It's 0.25. But the answer is 0.75.
Oh, okay. So here is a small thing that you have missed. So 0.25 is correct, but you have to see that in the question they have asked for Jaccard distance,
Yeah.
not similarity. So Jaccard similarity and Jaccard distance are two different things. So imagine that you have to, so conceptually, what is the difference between those two? Imagine you have two sets, okay, A and B. And if you are comparing how similar they are, how similar A and B are, then you will see how many overlapping elements are there in the two. Like how many elements these two sets have in common. That's a measure of similarity, right? So basically, if two sets have more elements in common, then they are more similar. If they have less elements in common, then they are less similar. So when you are doing intersection by union, so intersection means how many things are there in common, right?
Common.
Yes, common. Intersection means how many are there in both. So how many are in common? So it's a measure of similarity, how similar two sets are. So greater the value of that intersection, greater is the similarity and greater will your Jaccard approach 1, right? Because the intersection will start becoming like the union. More and more things are in common, right? Now, what is the maximum value of Jaccard similarity that you can get? 1. So what is the distance? Now, distance is an inverse notion of similarity. So basically, 1 minus similarity will give you the distance if the similarity score lies between 0 and 1.
Okay.
Right. So here what's happening? 1 minus 0.25 is 0.75.
Okay. That's
Right.
similarity. That's what.
Yeah, so this is the important term. So in machine learning and in these applications, this distance versus similarity is an important distinction.
Okay.
Right.
Then third question.
Okay.
Sir, I don't understand.
Let me read it. For any two sets Si, Sj, where H comes the family of min-hash functions, it is possible to construct a counterexample so that the probability of HSI equals to HSJ is different from the Jaccard similarity of Si and Sj. So I know this is false, but to explain why it is false, let's see how to explain this. Let me think a bit. So is it covered in the lecture notes? Let me just try to, because there is a proof of min hash which tells you that the probability of equal phi is equal to phj is the same as the Jaccard. So can you tell me the slide number or?
Jaccard slide number, sir.
Yeah. No, that min hash.
Okay, one. I think lecture 11, sir. Lecture 11.
Wait, so I am right now in lecture 12. Okay. ED trees, naive solution, application, nearest neighbor. No, this is nearest neighbor, right? So that means we have started hashing here. And then we have Mr. Price and all these. So min hash will be after hashing, right? Yeah, okay. So here I see Jaccard, eligible similarities. Why is
You're in week 2, sir, actually.
no, this is week 3, right?
Okay.
Okay, so we are at LSH and then we are looking at cosine and then direction is fine. This is okay. Okay, so this is min hash, right? Min hashing.
Min hash.
So we are picking a permutation of the set, and then what we are doing is we are just taking the first few, the first row where the two sets has a 1, we have the equality if both rows contain ones, which means that this row belongs to S intersection T. Now S and T are the same event. Oh, okay. So what here we are saying is, so what do we do in min hash? We just take the random permutation of the sets and we see the minimum element under that permutation, right?
Yes.
Yeah. So in any random permutation, if we have the same minimum element, which is basically this condition. So under S, under the permutation of S and permutation of T, if we have the same element, okay, that's what we are checking here, right?
Yes.
Right. So if they are the same, if we have the same minimum element, that means that it's a member of this intersection set, right?
Yes.
So if we randomly permute S and if we randomly permute T, what's the probability that they have the same in each first element, let's say? Minimum meaning minimum position. So which is the first element that we are checking? If they have the same first element, that means the elements are the same. Which means that it is an element which appears both in S and both in T. Right? Because the first element is the same for both. So it has to be a member of both the sets. Now, if we have these many elements like union of S union T, this is the total universe, right? So if we have these many elements, what's the probability that S intersection T element comes at the front under any random permutation? Do you understand? So, okay. So if you have not understood, let's discuss again. Should we? Should we, or am I over explaining things? Oh, okay, fine. Let's do it again. So we have a universe of elements. Some of those elements belong to S, some of those elements belong to T.
Fine.
Right? Now we have, let's say, S union T total elements in the universe, and we can permute them in a bunch of ways. Okay. Under those permutations, let's say any one of those elements appears at the first position. Okay. Now, if that element belongs to this intersection set, then this value will become true.
Okay.
Right? Only then. If it's some element which does not belong here, that means the values will be different for S and T under that permutation. Okay. So what's the probability of this being equal here? The probability of a intersection element appearing at the front.
It must be there. The intersection should be there. Otherwise, it will be false. That one.
Exactly. So therefore, by definition, it's only possible to have this probability as the equality here.
Okay.
So we cannot construct an alternative mechanism.
Can I say ask this S intersection that what should be the value for it? It should be it should be more or it should be less. Then only we can say that it's true. Suppose S is 100 and S intersection is 1, then 1 by 100, so that doesn't does that mean that probability of H of S equal to H of T?
Yes. Why? Because like you said, let's say S union T is 100, okay? And let's say the S intersection T is 1. So if we randomly perturb the elements in the universe, okay? So what are we doing? Let's say we have 100 elements in the universe, huh? And then we are permuting them in some random order, okay? Now, the elements of the universe which occur in S, they will be ordered according to that permutation.
Okay, fine.
The elements of the universe which are in T, they will also be ordered according to that permutation.
Okay.
Now this is happening. Now we are checking under the permuted S and T sets if the first element are the same.
Okay.
When can it be the same? Only in one case out of 100 in your example. Because only in that one case will it be the same element and will it be in the front.
Okay. Maybe in the front or it may be anywhere.
It may be anywhere, but under all possible permutations, it's still this 1 by 100 because the one element being at the front is fixed, and then you have 99 factorial mix up in the remaining positions. Right. And then you have 100 factorial mix up of the entire set.
Yes.
So 99 factorial by 100 factorial is 1 by 100. Right.
Yes.
So that's the idea. So basically under construction, this is the definition of what you know as Jacquard similarity. And so this equality will always be that.
Okay.
Okay. So this is something like that. Okay.
Okay, fine. Next question, next one. The theory question
okay. Let's try. Let me also sit with you. Okay. You claim to have created a deterministic hash function RD to K that is for every data set and for every query point. We can ensure that HQ contains only one point, which is the nearest neighbor of Q in D. Okay. Interesting. Your friend contradicts your claim by saying that the function H cannot be independent of the dataset D. Is he correct? So what we are claiming is we have a hash function which works for the dataset D, and for every query point, we know that this hash function HQ has only the nearest neighbor of the point.
Nearest neighbor.
So this function H cannot be independent of the dataset D. Interesting. Okay. It has to be dependent on the data because I see. I'm not sure of why we can say this is true always. Let me try for a minute. If the data is dependent. If it is independent of the dataset D, then that means that for any dataset, it always maps the query point to only the nearest neighbor in the dataset. Right? So if we have, okay, so here's a thought. Okay. So let's say we have a deterministic hash function. So the hash function is fixed, right?
Fine.
Okay. Now we know that given any query point Q, it maps it to, let's say, a query point P, which is its nearest neighbor in the dataset, right? So the hash function is fixed, the query point Q is fixed, and the query point P, which is given the hash function and the query point, is also fixed. So this much you are okay with, right?
I'm okay.
Okay, hash function fixed, query q fixed, and the p, because the hash function only maps it to one point, is also fixed. And it's a deterministic hash function. So it will always map q to p. Okay. Now in this data set D, p is the nearest neighbor of q. That is given.
Huh.
But let's say if we change the data set slightly and there is a new point, let's say x,
Okay.
which is closer to q than p. We can always do that. We can always introduce another point in the data set which is closer to the query than the current closest one.
Yes.
Right? Then, because it's a deterministic hash function, it will still keep mapping p to q, not to x.
Okay.
Are you convinced?
Deterministic.
Yeah. So because if we slightly modify the data set, it will no longer map the query to the closest point. If we modify the data set cleverly. So that's why I feel that it should be true.
Okay.
It cannot be independent of the data set.
Because it's fixed. Everything is fixed.
Yeah, exactly. Q is always mapped to a fixed point. Now, if we introduce a closer point, the hash function cannot handle that.
Because it's already
right.
And one more thing. In count which case you are saying this thing. Now, where should I run this program?
Where should you
run this program?
Oh, this program. Let's see what's required. You need NumPy. You have the count min sketch object, hash family, len hash family, value error, and then mat, add element, and then there is some. So you cannot actually run this because this code is not complete. But oh, okay, you have to fill in the thing. So if you want to actually run it, do you have Python installed in your machine?
Python.
And NumPy will be there definitely.
NumPy is definitely.
So then I think this. Okay, so then I think this should run in your machine.
This one.
Yeah. It only requires NumPy, nothing else, right? I am looking at the code. It doesn't need it. It's only using NumPy.0, which is fine. And then everything else is just basic Python code. There is nothing very. And in case you don't have this in your machine, you can always use Google Colab. Do you know how to use that?
Google Colab, I know. I have done it.
Okay. Then I think you can run it there.
Okay, I will do it. And this seventh question.
This one.
Yes.
Okay. If H is a LSH family, and for any hash function in the LSH family H, the true nearest neighbor of the query may still fall into a different bin than the query. So yeah, I think this is true. So why? So what is your question? Why would it be true?
So why it is true, sir? LSH, I know locality sensitivity happening. That near similarities, there may be a problem. So we can see through LSH. Yes, sir.
So the definition of the basic notion of LSH is that it is an approximate nearest neighbor search, right?
Yes.
Approximate is the keyword. Now, what happens if the true nearest neighbor is always in the same bin? So what are they saying? It is not necessary that the true nearest neighbor will be in the same bin, right?
Yes.
So what happens if the true nearest neighbor is always in the same bin? That means we can always guaranteed find out the true nearest neighbor, right?
Okay.
So that is not approximate. That's a like guaranteed solution. But you know that LSH is an approximate thing, which means that the query may be in the same bin as the nearest neighbor. The query may be in some different bin as well.
Okay.
So what do you mean by bin and all that? You understand, right?
Bin means you can say bucket.
Bucket. Basically, whatever the hash code, the output of the hash function is mapping that element to in that bucket. Yeah. So it may map the query to a certain bucket, but the nearest neighbor may be mapped to a separate bucket because it's all a very random process. It's approximate. It's not deterministic.
Okay, fine.
Right.
Sir, a question है इधर. आप week 2 में जाएंगे. Only one question.
No budget. You can ask as many as you want. Week 2, I see. Okay, let me also open the slides on the side in case we need it. Hold on. Okay.
Sir, question number, I'm telling you this one. Question number 8, I couldn't solve it. I tried, but I couldn't. Last week also, I had a problem.
Oh, I see. This one. Okay.
Uh,
So what did you try?
I have used this value. You told me that you use that over there in that formula.
Yeah.
But sir, I couldn't use. I don't know how to use, and I
Okay.
couldn't solve it, sir.
Let's try once again.
Please.
So let's open the slide to see the formula.
Okay.
Do you have the slide number?
Slide number.
Or I'll scroll. So Bloom filters is the one, right?
Yes. Sir, it's nearby also.
This one, right? Okay. So quick recap. Let's take a minute to recap. We have m buckets. We have n elements inserted into the bucket. And then the probability of whatever this hx equals to 0. One sec, please. Oh, wait, no, this one is not it.
This one.
Niche one, right? Yes. So the expected number of zeros is this m times e to power n by k. And then we have lookup. Okay, and then
This is the formula minus n by n.
yeah, so this false positive rate is log of 1 minus p to the power k, which is log of p and log of 1 minus p. Okay, got it. And then the minimum comes at this position and the optimal choice is this. Okay, so this is the false positive rate, right? And this is m and n. And we remember that it is ln, so log based e.
Log based, yes.
Right. So let's see by putting the values. Hold on.
One second, let me write the formula, then I'm going to put it. You will tell and I will put.
Okay, that's good. So let's just try this formula then. This is 2 to the power minus m ln 2 by n, right?
By n, okay.
Okay, so let's try. So let's say, wait, where am I?
It's wrong.
Yeah, okay. So length of the bit vector is 10n and the number of hash functions required is 7, 10n and 7. Okay, so bit vector and what is the length of the bit vector and the number of hash functions? Okay, so what is the length of the bit vector? Okay. Hold on. So sorry.
Left with n is the value of the bit vector.
That's what I'm confused. Let me just see. I thought it was the number of elements that are being inserted. Okay, so this is the number of elements that n is the number of elements that are being inserted.
Yes, that I.
Let me check the length of the bit vector. K is equal to 1 is.
Sir, m is the length of the bit vector. Size of the bucket, I think.
Size of the bucket will be 2 to the power bit vector, right?
Yes.
Size of the bucket. Size of the bucket will be 2 to the power the length of the bit vector, no?
Right. I've never seen this.
No, let's say you have 3 bits, then how many buckets are there for that bit?
According to 3 bits, so 8 buckets.
Right, exactly. So m, if it is the bucket size, then how many bits would be there? 2 to the
M is
power?
the bucket size.
Yeah.
M equal to 2 to the power of M. But M is the bucket size.
Hmm.
Okay. Okay.
Right.
Bucket of 1. M equal to 2 to the power of K. Sir, log use होगा. If you want to find the number of bits
Mhm.
to the bucket, so you use log I.
Yeah, yes, log base 2.
Log base.
So, one second, let me think about it. So here we have M is the number of buckets. So let me try to write it once.
Please do it.
Log 2 of M, and then okay, so M will be, let's say, log 2 of log of number of so M is number of buckets. So let's say you take a variable X, which is the number of bits. Okay.
Okay.
So 2 to the power X is M.
Okay. M equal to the power of X. Okay.
So therefore X equals to what? Log of base 2 of
Log
M.
of M base 2. M base
Log of M base 2, exactly.
Yeah.
So now M is 2 to the power X.
Yes.
Log of 2, which is, hold on. So now it's a, so you can replace M by 2 to the power X here, let's say.
Yes, yes, right. Yes.
Okay, and then let me look at the question. How many length of the bit vector and the number of hash functions? Where is the number of hash functions being factored in? Let me check that. Sorry. Lookup is this of HIX increased. We can find the optimal K. K is basically the number of hash functions.
Yeah.
So what is happening here to K? M is this, H1 to HK are the this thing. This is 1 by M. So here K we know. And in the formula, P is e to the power minus K N by M.
Sir, I am writing the formula. E equal to 50 power minus K by.
Yeah. Right. Okay. So here we have K and we have N, and you can replace. So try putting it in this formula, maybe. Let's see. So what is what are you saying? Sorry.
Number of hash functions.
So K is the number of hash functions.
So sir, we can do one thing, we can take log on both sides and find the K.
Right. So that's what we are doing in this next step, log of the false positive.
So log E equal to 1.
Yeah, yes, yes.
Minus K upon M log E. Log E is 1. Fine. Then K equal to, minus is there, minus later equal to M by N log E.
So we know K. So let's only take minus K N by M. So we know K. If we replace M by that 10N or whatever value, right, then the N cancels out.
Can you replace it? I'm doing it.
Yeah.
Equal to e to the power of minus K. Let's see the solution. I'm taking the answer directly now. Let me see what
Right. And we want 10%.
Okay, 10% is also there.
10% we want to be the answer. Okay. So let's see. 5n. 5n is 4 times n by 5n is equal to 4 by 5. And then what is the value of log 2?
Log 2.
Hmm?
I'm seeing in Google. What? Log 0.301.
0.3, right?
0.
So in this formula, if you put the values of k, m, and n, then you have k equals to 4. Right. Is equal to, let's say we have 10n log 2 by 5n, right? So what is, okay, no. We have 5n below.
5 is a bit, I think.
Oh no, sorry. We have, what is 5n? M is 5n, right?
Yes, sir.
So 5n log 2 by n. So 5 log 2 is?
Yes. 5 log. 1.5.
Oh no, it's not matching. Okay, I have to see this for a bit. I think what's happening here. Let's try for 1 more minute, otherwise I'll ask the prof.
I think it's okay.
So let's see. We have m, which is 5n. We have, what is 5n? Let's see. Length of a bit vector. Length of a bit vector is 5n. Then there will be this is n into log 2 by n 4. Okay, no, so what I'll do is, instead of spending more time here, I'll ask the prof and then I'll post the answer in the discussion
Please,
chat.
sir, it's a request, sir. Please,
Fine.
post.
Okay, I'll give the solution for this.
One, a basic question.
Hmm.
Can I ask? Sir, one more. Yeah, regarding stochastic gradient distance.
Regarding?
Stochastic gradient distance.
SGD, okay.
SGD.
Hmm.
One second. Sir, suppose there is a random starting point, okay? And from there, I want to convert to a global optimum, means minimum point.
Right.
Okay, sir. And step size eta t.
What is eta? Learning rate. Step size.
Step size.
Okay.
Step size. And iteration t. Step size and iteration t. Eta t.
Okay.
Okay, sir.
Then,
sir, what will be the condition that guarantee that the SGD will convert to a global optimum?
What is the condition that will guarantee that SGD will converge to a global optimum? The SGD will converge if the function is convex. That's the only guarantee.
That's the fine.
Uh-huh.
Now, if I go like that, then eta t is greater than 0 or equal to 0, what is numerical, what will be the, can you please explain this thing, that how it's happening? Global optimum, how it's going in?
So no, I am not. So sorry, I am slightly missing the question. So what are you asking? How SGD works? Or
Sir, what I'm asking that the question starting from a random starting point, any point, okay?
Okay, any point, fine.
What would be the condition that would guarantee that entity will converge to a global optimum? Okay.
Okay. So
assuming eta t to be the step size at interest and nothing else.
Right. Okay. So the eta, the step size has to be some value greater than 0, right?
Greater than 0.
It cannot be negative.
Okay.
So basically, what SGD does is first it identifies the direction of the greatest, descent, the direction in which the loss function reduces the most. And then it decides how much to move in that direction, right?
Left or right, but negative or positive.
So if you, no, not negative. If you make it negative, then it will move in the opposite direction.
Yes.
Right? So it cannot be negative. It has to be some value which is positive. So in practice, whenever we set these step sizes, this learning rate or step size, we always set it to some value greater than 0. So it is usually 1e minus 3, like 10 to the power minus 3, or maybe 10 to the power minus 2, 10 to the power minus 4, some small value which is greater than 0, but it should be positive. If it's negative, then it will go in the wrong direction.
Sir, what is the list? Eta t and interest. That step size and interest. What is the list?
What is the
relationship between step size and interest?
Oh, okay. So basically, no. So in many applications, the step size was fixed, no matter what iteration it is in. Okay. It used to be the case in earlier algorithms for gradient descent, and then people figured out that we want some adaptivity, right? If we have more number of iterations of the so T is the iteration number, right? So if we have been training for longer and we have a history of the gradient updates, we have a history of how much the gradient has been updating in time from 1 to T. Then we also want to factor that in while deciding the learning rate or the step size at the Tth time. We want to make a more intelligent decision. So that's why they call it eta t. Otherwise, in a few years back in the earlier versions of this algorithm, it used to be some eta, which is independent of t. It's
independent of interest.
Yeah, so it used to be that, but now so what happens is when you so let's say you are starting at some random point and after a certain t iterations, you are approaching the global minima, right? So as you are now approaching the global minima, you want to slow down. You want to take smaller step sizes and you want to move more carefully. So that's why you see usually in practical ML applications, the learning rate is reduced as the number of iterations are increasing, because as it approaches convergence, you don't want it to overshoot. If you have the constant fixed learning rate, what used to happen was that it used to exceed. So if imagine it's going down a slope and it's reaching the bottom of the slope. And if you have the same speed as it's approaching the bottom, then it will go to the other side. Yeah, it will overshoot and then it will come back again and there will be this ping pong motion. So in order to avoid that, as you approach the bottom of the slope, you slow down so that you move little. The step size is smaller and smaller as you go towards the end, and then it converges faster. That's the only reason. Otherwise, earlier they didn't use to factor in t for learning.
One list. I have gone through eta t less than 1 by t square.
Eta t less than
1 by t square, 1 by root t.
Okay, so where did you see this?
Sir, in the lecture only.
Okay, so this is possibly one of the heuristics for these modern optimizer. We have to see.
Okay.
There are a few different heuristics which are like people have proved that they work quite well. So 1 by t square, if you have eta t is equal to 1 by t square, what does that do in practice? If t equals to 1, then it is 1. If t is 2, it's 1 by 4, so on, right? So as the t increases, it keeps reducing, the fraction becomes much and much more smaller. So intuitively that makes sense, right?
Sir, actually what happened, I was searching two questions from IIT. Okay,
Okay.
IIT Kharagpur.
Mm-hmm.
So I have got one practice problem, optimized. Okay.
Okay.
Scalable data mining. The name of the paper is scalable data science, not data mining. Okay.
Okay. Okay.
And over there, this question I came across this question, and here they said that with relation should be eta t less than 1 by t square, 1 by root t. So which one will be, sir? Which one will be appropriate? This one or this one?
So, okay, so let's see. So I am also hearing this question for the first time, but let's reason it out together. So if it's 1 by t square, then what's happening? It's going from 1 to 1 by 4 to 1 by 9 to 1 by 16 and so on, right? That's its slope. And if you have 1 by square root t, then what's happening? It's
one. जैसे 1 by 4, 1 by 9, 1 by, तो ये तो step size small होते जा रहे हैं, जितने आगे जा रहे हैं step size small हो रहे हैं.
small हो रहा है and ये exponentially small हो रहा है. This is becoming small exponentially because 1 by 4 is very small, 1 by 9 is even like very soon, like 1 by 10 tak it will become 1 by 100, which is like super small compared to 1, right? So this is reducing very fast. In the other end, if you have 1 by square root of t, then what happens? You start with 1, then you have 1 by square root of 2, let's say. At the fourth iteration, you have 0.5, 1 by 2. At the ninth iteration, you have 1 by, so it's falling, but it's falling much more gently.
Yes, sir.
Right? So among these two, I would say 1 by square root t is better because it's falling much more gently.
Sir, can I share the screen? I want to ask you a question.
Can you share screen?
I want to share the screen.
Okay. I don't see why not. So I have stopped presenting. You can share now. So the best way to ask these type of questions is to share the PDF of the source and just ask it in the chat.
I'm sharing the PDF of the source.
Yes, of course. I encourage you to do that. Then the prof can also take a look.
Okay. Sharing, sir.
Yeah, please go ahead.
Sir, I am here.
Okay, so should I share the screen then? Let me share the screen. Yeah.
That will be better.
Yes, you can see the screen, right?
I have my question, sir. I have it.
So tell me which one, this one you are saying.
So yeah, when minimax becomes equal data set size, it becomes a distant vector. Addition of momentum term is expected to reduce number of updates. Sir, this also.
Sorry, which question are you reading?
First question.
Oh, first question. Okay, okay. Okay, so let's read this. Consider the following statements about SGD being true, about SGD true. When mini batch size becomes equal to dataset size, SGD becomes a descent method. So when mini batch size, you understand mini batch, right?
Mini batch I know, sir.
Okay.
Small dataset I'm taking from a big dataset, and I work.
Exactly. So when mini batch becomes equal to the dataset size, then that is just your simple gradient descent.
Yes, sir.
There is no batching, there is no stochasticness.
Nothing.
So the stochastic part removes, so only GD is remaining. So that is gradient descent. Okay, so that is true. Addition of the momentum term is expected to reduce the number of updates. So Yes, I think that is true because you understand the concept of momentum.
Sir, it's I have studied, sir. अभी तो मैं भूल गई उसको तो
No, no. So it's a very intuitive concept. So basically, momentum means what? So let's say your gradient descent has been happening for some iterations, and it has been reducing in the same same direction for a certain number of steps.
Yes.
Then the model sort of gains confidence that this is the way to go, and it starts taking larger and larger steps, right? So momentum meaning you think of it in the real world sense, the speed increases, velocity is increasing. Because it keeps going in the same direction, it's gradually taking up more speed.
Yes.
So that's the basic intuitive idea behind momentum in gradient updates. And because it is gaining confidence and it's like taking larger and larger steps, then the expected outcome is that it will reduce the number of updates, right?
Yes.
Because it's taking large steps. So the
Yes.
hope is that it will converge faster.
Okay.
Right. So
Obviously, sir. With this, speed is adding momentum, speed is increasing. Simple. We get that.
yes.
Sir, second question, sir. What two questions are only these three, 2-3 questions? Rest I will do it on my own.
No, okay, but yeah, let's see. Let me also see. SGT update for a parameter for regularized linear regression. So I don't know if these are part of the syllabus, but anyway, let's try. So stochastic gradient descent update for the parameter W for regularized linear regression is given by the loss function, below. Okay. So what's the difference between A and B? WT plus 1, this eta is common, and then there is 1 by n. Okay. So in SGD, we are only taking one single data point, right?
Yes, sir.
So here n denotes the entire data set.
Yes, sir.
So there we don't, in SGD, we don't compute gradient over the entire data set. We only compute it over
Each data set.
Yeah, each
One data
each
set,
data
one.
point. So yi and xi will be there, nothing else. And then if you take the gradient of this, derivative of this, then what is it? It is minus 2 of this entire term times the del by del w, which is basically gives you xi. So it's giving you the minus this times xi plus this norm w square. This gives you 1 by 2 of whatever w times lambda.
Yes. L1, L2, no. This one is that.
This is L2 norm. Right?
L2, no.
Basically, it is W transpose W.
समझ आ गया.
Yeah.
ठीक. थर्ड वाले क्वेश्चन से छोड़ दीजिए, समझ गए.
Okay.
समझ आ गया.
So what is the following? Oh, this is what we have discussed, right? Okay, given the following learning rate schedules are guaranteed to result in convergence in the, so this I have to like ask the prof again, what does in the expected sense mean? Or I have to like study on my own. But between these two, I feel that you're right. Here there is, let me check once. So 1 by E. So I'm making a note of this. I'll update this question in the chat.
Okay.
This, I don't want to answer without being sure of the answer. Sure. Okay. So I'm making note of two questions, this question and the other third week's thing.
Yes.
Yeah, these two I will update the answer soon.
Okay, sir. And sir, one more simple question. Okay, sir. That mapper reducer, I think you know about it. That 627 we are going to be get along. Okay. Is mapper reducer का इन्होंने जो ये दिए, what is that coding दिए? Where I have to run this thing? Scalable run कर पाऊँ sir? It's not possible. Scalable में कोशिश किया.
Oh, अच्छा, नहीं. You are not supposed to run it per se. You just logically just analyze what's going on. Do you want to try to run it?
Yes, sir. I am trying it. Because I want to learn. That's why I thought that run. So देखो क्या हो रहा है.
Okay, so let me then discuss with the profs. Maybe we can have a demo on this Scala thing next week.
Yes,
We can show you how to run the code.
Actually, and I want what I want, sir. I'm telling you frankly, sir.
Hmm.
We do not want to install that Scala or that map reducing thing on it. So online, I want to do everything.
Okay.
Online compiler. There only I want to run, and I want to.
Okay.
run
So
the code.
okay. So let me discuss with the team and let's see how we can easily demonstrate that and have you run it. So yeah. Okay. That's a good request. Let me take it in.
Sir,
So,
unless we run it, no, we won't. That concept won't be clear.
No, fair enough. Fair enough. Let's plan for that. So, but give me the code that you would like to run, like week 7, is it?
Week 7.
Week 7.
Week 6.
Week 6. Okay.
Yeah.
Week 6, assignment 6, right? This question 9. No. 10th. Okay. Okay. Fine. I'll see. I'll see what setup can be introduced online to have you run this. Fine. Okay. Okay.
Roy, sir, one more request.
Okay.
Sir, I think only one problem session I will be getting. Sir, please make it two classes active.
Oh, okay. No, so that's what we are saying. So if you want live, that's fine. But I would request you to post any questions immediately in the chat. We are always monitoring it. So you can access the chat, right?
Yes.
So this is the discussion thing, like you had posted about this. Even if in the middle of the week you post, we will immediately give a solution to that.
Okay.
And if it's not enough to write it and just explain it, then we will upload a video or we will call you or whatever. That we will arrange.
Done.
Okay. But please post here first and then we will see.
I will do it. Thank you, sir. That's all.
Definitely. Okay. So I have taken a note of your requests. I will convey them and then we will check one second.
Yes, thank you, sir.
Okay. No, very much thanks for engaging and please keep it coming.
Sir, I am out of IIT, but I want that I should learn, I should be in IIT. In that form, I am studying this paper. Now I have taken it very seriously.
No, yeah, please do. You are on the right track. Please keep studying.
Okay. Thank you, sir.
Okay, thank you.
Bye.
Okay, so it's 8:05. So others also, if you have any doubt, please post it in the discussion. We will immediately answer. And for today, we are going to adjourn and the recording will be up on the YouTube channel, like always. Thanks. I am turning off the recording now.
Thank you.
Thank you.